Now we have seen different elements of quantum computing. First, the quantum register, which is composed of the different qubits, the fundamental units of information, and then the quantum circuit, which contains different gates in a specific sequence to operate and manipulate the state of the qubits in a specific way corresponding to a given quantum algorithm, and how to retrieve this via the measurement. We have seen also the 1-qubit gate and the 2-qubit gates and how to perform mathematical operations to represent the action of this gate on the state of a single qubit or 2-qubit state. Now we are gonna explore more the Hilbert space, and what we have seen so far is how to construct the Hilbert space of different qubits. So if you have 2-qubit quantum computer, each qubit is in the ground state, then we can use a tensor product to represent the state vector, which represents the state of this, or the combined state of the total Hilbert space of the 2-qubit system. And in that sense, if we use this tensor product, as we have seen earlier, we get the kit 0, 0. So this column vector, which has 1 here, represents the state of the 2-qubit system in the computational basis. So this is the Hilbert space of 2-qubit system. It is a 4-dimensional complex vector space, and the states can be labeled as we see here in the table. So here we see the ket 0, 0, the ket 0, 1, the ket 1, 0, and the ket 1, 1. 4 states because we have 2 to power n states. N here is 2 qubits, so we have 2 to power 2, which is 4. And then these are the labeling of these states or dimensions of the Hilbert space. And since the 2 qubits are initialized to the ground state, then we have one coefficient, which is 1, at the ket 0, 0, and the rest contains zeros. So in that sense, we can look at the state of the 2-qubit system initialized in the ground state. Both of them are in zeros, so we have the coefficient at the situation where both qubits are in 0 and 0 states. The other situations, which are probable because they are allowed in the Hilbert space, 0, 1, 1, 0, 1, 1, they exist, but they have 0 coefficients. It means that these situations do exist in the Hilbert space. However, they don't exist, or the state of the qubit is not containing any of these situations. So they are not probable at all. So we have one as definitive 100% probability to find the 2 qubits when we measure in 0 states, and the rest we will not find them. However, they are still allowed to be, if we do another operation, we can see them in the Hilbert space. Here there is a clear distinction between the definition of the space and the definition of the state. So the state can contain one situation, like the 0, 0 situation here, while it doesn't not obtain, or it doesn't contain the rest of the situations, the 0, 1, 1, 0, and 1, 1. However, the 4 situations are the dimension of the Hilbert space of the 2-qubit system. So they are there, but there is no projection of the state on them. There is no component from these other situations in the total state of the 2 qubits. So hopefully now we have the clear distinction between the definition of the state. We have one state, ket 0, 0, and the total Hilbert space, which has these 4 dimensions. It is similar to the analytical representation, x and y. Our space here is 2D, so we have x and y dimensions. So if you have one state which lies on the x-axis, then this state A is composed only of this projection. However, this is only the definition of the vector. The space itself is still 2-dimensional, so this didn't shrink the dimension. It's only that the total composition of this is made only of the x-axis. Here we see different examples, which we have seen them earlier. However, we are now applying the Hadamard gate in this example on the first qubit, and then we don't do anything to the second. So if we wanted to construct a matrix that acts on a 2-qubit state vector, this matrix should be 4 by 4. So this is why we act with the Hadamard gate on the first one and the identity on the second one. And together, the tensor product of both will give us the total matrix representation of the Hadamard gate acting on the first, while the identity acting on the second. And then if we do this action, we are gonna see that the superposition now happens here. So we act on 2 qubits initialized in the ground state, Now we see that the first qubit has been put in a superposition. So the situations where the first qubit is now presented to be in 0 and 1 has the coefficient, have the coefficients 1 over root square of 2. So we have 1 square of 2 next to ket 0, 0, and 1 over root square of 2 next to 1, 0. So this is a circuit representation, and we can see now if we look at the first location of these two qubits, we see that from the first location that the first qubit is now presented in the superposition. So it can be in a situation where it is 0, and it can be in a situation where it is 1, while the second qubit is still remaining in 0. So this is how we see or we analyze the Hilbert space. So we were in the ground state, but now we are in a superposition for the first qubit. So this is why we have the coefficients now appear next to ket 0, 0, and the coefficient appears here next to the ket 1, 0. For that sense, we have 0 next to the rest of the situations because they don't exist basically. They don't exist for the state that represents the two-qubit system. However, they do exist in the Hilbert space. So this is our Hilbert space representation. It is four-dimensional space composed of the 4 dimensions ket 0, 0, ket 0, 1, ket 1, 0, ket 1, 1. However, the coefficients next to this ket 0, 0 and the ket 1, 0 represented what happened with the action of the Hadamard gate, and the rest of the situation is still 0. We can check the normalization, and the normalization would mean that the total probability, which should equal to 1, the probability of all possible states should equal to 1. So this is a normalization condition. You get each coefficient, you square it in the ways that we have seen before, and then when you sum, you should get 1. With that, we have cleared how the Hilbert space is constructed and how a quantum state of a single qubit or multi-qubit, like two-qubit system, is represented and expressed in the Hilbert space.